And our last speaker this afternoon, pleased to introduce Samantha Patrick from the Marine Biology Unit, or Earth, Ocean and Ecological Science Unit of the University of Liverpool, talking about wandering albatrosses.
Thank you very much. So 10 years ago, I got a lift home from my field site with the CTBTO crew who were there installing a new hydrophone. And we came up with this idea on the boat. So it's really lovely to be able to come back 10 years later and tell you about what we found. This is also the first conference I've ever been to where I don't know how much people know about birds. So I thought I'd start with a little bit of natural history. So seabirds are the ultimate globetrotters. They're highly pelagic, they're long-lived, they're mainly monogamous, although a little bit less than the BBC will tell you. They're very slow to mature, so most birds have one chick per year. These birds might then go to sea for up to 8 years before returning back to land to breed. And they're highly reliant on land, so they can only breed on land. So even though they go to sea to feed, they go to sea to migrate, they'll always return back to land. And they cover huge distances. So birds cover large distances both while they're breeding, and then also in the wintering period, birds will leave their breeding grounds. They'll travel distances to find better areas where they migrate and overwinter, and then return back to their breeding areas. And so what this means is they have to cover very large distances over the ocean, which is seemingly featureless to us. So how do they find their way, and what does it look like when they go to sea? So when seabirds are at sea, they're doing one of 3 different things. When birds get to an area that's highly profitable, they'll start to forage, and this is seen in data when birds start to turn in circles. So birds will fly in circles when they're searching for food. They'll then rest, so when they're full, they'll rest on the water, or they rest on the water at night. And then thirdly, they have traveling behavior. So the traveling behavior is when they want to get from A to B, and this is easily detected because they fly in straight lines and they fly very quickly. So how do birds know where to go? Birds need to have information in order to find the areas that they're looking for. So over short distances, they need to be able to find food in localized areas. Over medium distances, they'll need to find these patches of food. And over large distances, they need to be able to find the areas they want to go to, whether this is where they're breeding, where they're wintering. And it's not just finding these areas that's important, they also need to minimize the costs of getting there. So they have to get where they need to go, but they need to get there using the minimum amount of energy. So for this study, we used the wandering albatross. So wandering albatrosses are the largest seabird. They can weigh up to 12 kilos, and they have a wingspan of about 3.5 meters. They're hugely wide-ranging. So in a single foraging trip, a bird might go 10,000 kilometers during the breeding season. They might circumnavigate the globe several times during the winter. And it's been estimated that during their lifetime, they'll fly the same distance as to the moon and back 10 times. They're also highly endangered, so understanding their behavior is also really important for conservation. And because of their size and their body shape, they're highly reliant on winds to minimize costs. And what they do is they use these windy and waving areas to soar, which minimizes the amount of flapping they need to do, and this minimizes the cost of this traveling.
Next one. Clicker.
Okay, so what do we know about the way that they can find their way around? So there's 4 different ways that people think that albatrosses might be able to use cues in the environment. The first way is vision. So just like humans, vision's highly informative. And so if albatrosses can just see where they need to go, this is probably their dominant cue that they would use. They also can smell. So albatrosses and petrels in particular have really good sense of smell. And certain areas of the ocean which are really profitable, that might have certain types of marine organisms, will release compounds, and we know that birds can smell their way towards those areas. It's also suggested that they might be able to use magnetic cues, and we also know that they might be able to use hearing, but all we know about this so far is on very small scales. So we know that if birds are up to 1 kilometer apart, they might be able to hear other birds. So they might see that they're feeding there, or they might be able to hear their calls. But what we know is that all of these cues have their limitations. So what you can see on this figure here is that while vision's important, it's probably only useful up to about 30 kilometers. Some other work we've done has shown that birds can fly towards fishing vessels at up to 30 kilometers, but when the boat's further away, they can't fly towards it, suggesting that's the limit of their vision. Olfactory cues might be more useful over larger spatial areas, but they tend to be very heavily affected by winds. So this means that they can be unpredictable in certain situations, and also that they're not great for very long-range cues because they'll dissipate with the winds. Magnetic cues are useful, but the magnetic field of the Earth is relatively fixed. And so whilst it's useful for a bird to be able to orient, to know whether it's going north or south, it's not very useful to be able to tell it anything about the dynamic environment. So what we have dynamic short-range cues that the birds can use, and we have fixed long-range cues. But we lack a dynamic long-range cue that a bird could use to be able to navigate its way over long distances to look at environmental variables that are changing in space and time. So why might infrasound be important? So earlier on in this session, we had a presentation about microbaromes. And we think that infrasound might be important because it might be able to help birds identify land. So it might be able to help them orient and fly back to their breeding colonies. It might be able to help them find optimal weather conditions. So they like weather conditions that are windy and wavy, although not too windy and wavy. And they also like upwelling zones. So upwelling zones where the water's brought to the surface are highly productive because the food's brought to the surface and the birds can then forage on it. So marine habitats microbaromes are an important source of infrasound. And these microbaromes are associated with waves colliding together or waves hitting shorelines. And because they're generated by strong winds and storms, this is a potential source of really important information for albatrosses. And it could be an indicator of long-range weather conditions, and it could also be able to be used to identify profitable areas. So to look at this, we used 89 wandering albatrosses. So we equipped them with GPS loggers. So these are just loggers that you might use for sports, or they're just things that you get off the shelf. So we take them out of their box, we waterproof them, and then we duct tape them to the back of the bird on its feathers. So we deploy it when the bird's on the nest, we let the bird go to sea, and then when the bird returns, we take the device off and we download the data. And so from this, we have behavior every 15 minutes of the birds while they're at sea. And what I was talking about earlier was we're really interested in these traveling sections. So we're interested in when the bird is making a long distance movement, and these are the areas, these are the sections of the track when they're flying straight and they're flying quickly. On the map here, you can see the tracks that we had. So the green are the females, so the females go north of the colony, and the yellow are the males, and they go south of the colony. And in the top left, you can see South Africa, and in the bottom, you can see Antarctica. So you can see just how wide-ranging they are. So what we did was we combined this with microbarom soundscape maps, and what we wanted to know was we wanted to estimate what was the microbarom experienced by the bird at a point in space and time. And so to do this, we also combined it with wind data. So we used ECMWF wind data. And from this, we looked at the speed and the direction of the wind. So every time we had a position where a bird started this directed flight, we called this a decision point. And then we looked at the direction that the bird flew at that point in time. So here we have our albatross. And what we did was we created 6 segments around the bird. We looked at the segment that was chosen by the bird, and we compared that with the other segments. So we used a radius of 2,000 kilometers around the bird, as this captures about 95% of the microbarom signal. And we integrated the infrasound across those segments, and then we compared the conditions in the segment the bird chose compared to the segment the bird didn't choose. And this allowed us to ask whether the birds choose segments based on infrasound and wind. So the first result we found was that albatross movement is linked to wind. This has been very well reported previously. So just to understand the results a little better, I've put this schematic just so you can see. So a headwind is a wind that blows straight into the face of the albatross. These are not great, and they tend to be energetically costly, and birds don't like them. Tailwinds blow into the back of the bird and can help it move along with minimal energy. So birds tend to prefer tailwinds. So here you can see on the figure, we're just showing you the results for males, but the results for females are very similar. I thought it's just easier to just show you fewer graphs. So on the x-axis, we have the wind direction. So we have the tailwinds on the left in pale blue, and the headwinds on the right. And then on the y-axis, we've got what's called the odds ratio. This is just the chance of a bird choosing a segment. So the higher you go up the y-axis, the more likely a bird is to choose that segment. And what you can see here is that in tailwinds, birds seem to be more likely to choose a segment. But this is most important at high wind speeds. So on this graph here, the high wind speeds are shown by the purple line. And what you can see is there's a really strong effect in high wind speeds and in tailwinds. So this means that birds like tailwinds, especially when the wind is strong. So what about infrasound? So this figure here is similar. So we have the estimated odds ratio on the x-axis. And if you're to the right of the line, then that means there's a positive effect. To the left of the line, there's a negative effect. And if it overlaps the line, there's no effect. So the first and exciting result we found was that as the sound pressure level increases, there's an increased chance of the bird choosing that segment. And this showed that birds move towards areas of higher infrasound. Next, we thought that wind speed would be important because it's important for other areas of flight. But what we found here was that as the wind speed increased, it didn't affect whether the bird chose the segment or not. So the wind speed didn't affect the selection of the segment. But what we did find was a strong interaction between the wind direction and the infrasound level. And I'll show that on the next slide. So in tailwinds, which are shown here by the blue line, as the sound pressure level, which is shown on the x-axis, increases, the probability of choosing that segment also increases. And that's this blue line that you can see increasing in slope. However, when you look at headwinds, which are shown in the green line, as the sound pressure level increases, there was no change in the propensity to choose that segment. So what are our take-home messages? Well, first, we think this is the first evidence that birds do respond to infrasound. People have speculated in the past that birds may use infrasound to avoid tornadoes, or birds may use infrasound for other reasons, but this is the first time anyone's actually been able to show it in the wild. It does suggest that infrasound may be a long-distance cue for movement, but there's a lot more to do. We need to look at the scale at which birds are integrating the infrasound signal. And what would be ideal would be to study the other cues that birds are able to use to see which of those are being used at different time points. Third, wind direction is crucial, so this is really important. It suggests that birds are only willing to make decisions when the wind is good. So birds will move towards areas of higher infrasound when the wind conditions are optimal. But when there's headwinds, birds don't make those decisions, suggesting that headwinds prohibit those kind of movements. And finally, this is just the start of us understanding the importance of infrasound for animal navigation, and I hope that there'll be many other people using the CTBTO data to investigate it.
Thank you very much, Samantha. A fascinating study. Any questions from the audience? Yes, please. Can you?
Hello. Thank you for the presentation. I have a question. You said that the albatross may be sensitive for infrasound. As you know, the infrasound waves travel long distances because they are trapped in the atmospheric waveguides, especially the stratosphere and the thermosphere. Now we are talking about an altitude above 10 kilometers. And what I know that such kind of bird cannot go more than 1 kilometer, 2 kilometer maximum, I think. So now we cannot talk about infrasound for long distance. As I said, the main waveguides are so high. So I think the albatross is sensitive to the wind direction more than infrasound. Than the infrasound.
Yeah, I mean, I think it's a really good point. I mean, the reason to model the wind direction and the infrasound simultaneously is we can control for the wind direction, so we can control for the effect of wind, and we look at an additive effect on top of that. You're completely right in terms of how the birds that only fly maybe 10 meters above the surface experience infrasound in the way that we know. So we've been doing work, part of the project designed some new loggers that are able to actively record infrasound on the bird, and that's something that I think is going to be really important. So if we want to know what infrasound the bird's actually experiencing, the best way is to record that on a device on the bird, and I think something like that's the best way for us to understand better exactly what they are using.
Thank you. There was a question in the middle, I think. Yeah, you've got a microphone.
Yeah, it's kind of a side question, but when you mentioned long-range navigation cues, I didn't hear you mention use of sight to astronomical observations. And I seem to remember years ago there were experiments putting pigeons into a planetarium and got positive results. What's the current thinking on that?
Yeah, there definitely have been, and there are other navigation cues that have been suggested, so I focus mainly on the kind of the ones that have been very well supported, I suppose, or the best discussed. I don't know that there's been much work recently on that, but I would have to have a look. But yeah, there certainly has been some work in the past, and also work looking at sun compasses as well.
Yeah, thank you.
Any more questions? Oh, if this is really a question rather than another comment.
Yeah, this is a question. Do you have an idea or to do a study on the behavior of the albatross when passing close to infrasound sources? I think this is important if you look to the behavior of the albatross when crossing an area where there are volcanoes or something like this, maybe give you an idea about his sensitivity about infrasound. Do you have such kind of idea or not?
It's not something we're doing at the moment, but the seabird tracking database is a huge resource which is also openly available. So it's possible that if you could find the data, so we did talk about this in the past, if you could find data where birds have been tracked simultaneously to when you have volcanic explosions, then you may well be able to look at whether there's changes in behavior. But it would require quite a good time match in terms of birds being in the right place at the right time and having loggers on. But I think it certainly is, it is interesting, but I guess one question would be, why would they respond to volcanic eruptions? I guess we don't have such a strong biological prediction for that as we did for the microbarium infrasound.
In the interest of time, I think we probably need to finish the questions on this talk. So thank you, Samantha, once again.